Hey everybody, this is Larry. This is day 20th of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's poem. Today I ran bridges, which means that I go up and down a bridge for 4 miles ish and a couple more miles sandwiching it. I'm very tired, ready to pass out. And today we have a hard problem, so anyway, I hope everyone's doing okay. I'm still just trying to get back in shape. Like, I'm not really running that fast or anything, but yeah, let's take a look at today's poem. Today we have 3108 minimum cost walk-in weighted graph. It's a hard poem. You have an undirected weighted graph. Okay, you're given the edges with a weight. Okay. A walk is a sequence of vertices and edges, okay. A walk starts and ends at a vertex, and each edge, okay. Can visit the same place more than once, okay, so it's not a simple path. The cost of a walk starting at U and end at V is defined a bitwise N. That's weird. Of the way of the edges traversed during the walk, okay. It's a bitwise N, so that means that it only gets smaller, right? So I think that's the... Okay, you're given 2D array query. You have to find the minimum cost of the walk starting at vertex x sub I, and okay. If there's no such walk, return -1. Okay, I think this is a case analysis problem, it seems like. So what happens if two edges are connected, right? For a connected component. Or two nodes, sorry, not edges. But if you have two nodes that are connected, then in a greedy way, because you're trying to minimize the cost, you're going to try to get as many nodes as possible, right? I think that's it. And the only way, and so basically, and it always benefits to hit every node in that entire connected component, right? So then the query just becomes connected component things, and as a result, probably union find problem. And of course, if they're not connected, then it's a -1. So pretty, honestly, feels pretty okay. So let's get started. For UVW in edges, we have let's just say adjacency list of U and VW, right? UW, right? See this? It's spelled default correctly, right? And now we just want to construct a connected components thing, right? I said union find because for some reason I was thinking directly. I mean, you have connected components. You can definitely do a union find. It's not that tricky. Yeah, I guess so. I mean, I'm trying to think whether it some stuff in my eye. You go to. I mean, you don't have to do union find, right? It's a connected component. I'm just thinking in my head which one makes more sense. I mean, it doesn't really matter. So let's actually do it with depth first search. I feel like connected components is probably how I would have done it in the past. So maybe not, but we'll see. So yeah, so we'll try something new today. And here maybe we'll have a wizard, right? Maybe we'll have the current node. We have the parent node, the current rate. Yeah, and I think that we're good, right? Maybe the root, just to kind of have it to mark something, right? Actually, we don't even have to, really. Actually, the current weight doesn't even it's not necessary, right? We just have to mark the colors. Yeah, I mean, we could do it in a number of ways, but right, so yeah, because we don't have to do it in one pass is what I mean. So yeah, so here what we want is something structured like for I in range of n. Is it 0 indexed? and oh yeah, the reason why it is 0 index, by the way, but the reason why I don't look at the n is because I know that if I'm doing what I'm doing, I know that it's going to be linear, and if it's linear, it'll be fast enough. That's why I didn't really look at the constraints. But yeah, so here, if not visited I, then we just visit I -1, right? Something like that. And then we have visited is equal to force times n. Yeah, and I don't know what was the maybe this isn't the cleanest way, but that's fine, right? So maybe here we have current is equal to an array of stuff, right? Just so that we keep track of what's going on here. We append node, right? Then for we in and the rate, but we don't use the rate yet. In adjacency list of node, we just visit we and the current node, right? Oh yeah, and of course, if v is not equal to parent, so we don't bounce back and forth. And also, if it's not and we haven't visited yet, we and here we visited node is equal to true, right? Something like that. And then now we can yeah, and then now we can go through current and then we just set it, right? So here, how do I want to phrase it? Yeah, so maybe we have like a cost dictionary. You have the root will be every node has a root, so we can use an array here as y. So for x in current, root sub x is equal to I, right? And the cost will be the weight of that component, right? So we start weight with oh, did I mess up? Oh, it's on the edges, not on the nodes. Okay. I mean it's the same idea really. It's just that you look at all the I messed up though. I mean, we have to restructure a little bit because for some reason I thought the weight, even though I know that I wrote it out, but in my head I had the weight on the edge, on the node, which is, and then I just go through all the nodes and then kind of do the bitwise and that's what I would have done. But otherwise, yeah, I mean, I don't think that's that bad. I mean, maybe instead of, I mean, current is fine. We can also, no, I mean, we just look at all the node. So for every node, we just look at every edge that is outgoing, right? Because we know that we visited all of them. So for rate in adjacency list of x, we want to do a bitwise and so we start the total rate, TW for total rate, is equal to just, what is the biggest number? Rate is 10 to the 5th, so we'll just, that's a million, I mean it's less than a million, but we'll just do a million, which is 1 to the 20, so 1 to the 20 minus 1. The reason why I have minus 1 is that so it's all ones in the bits, right? And then here, we just do because here's, I mean, same idea. I know that I said a little bit different because I was assuming a little bit different. Is that instead of going visiting all the nodes, which you still have to, but you also want to visit all the edges because in this case, for example, you want to both go to 1 and the 6. You know, actually, and they tell you that in example. So yeah, so you have to go for all the edges, and then now, yeah, that's pretty much it. Costs of what you gonna call it, I, which is the root, is equal to TW, and that's it. And then query is pretty straightforward for UV and query, right? So then we get the root of U, root of U, root of V, right? So if RU is equal to RV, right, if the roots are the same, then we just that's a pen, not so cost of RU, else we append -1, and that's it. I mean, we have to set it obviously, but I think that should be good, right? And like I said, this is linear, so I'm not going to really worry about the complexity, unless I made a mistake with respect to implementation. But I'm actually surprised that we're that slow. Is there a faster way? I mean, I guess 10 to the 5th recursion, maybe it's a little bit too many things on the stack. I don't know. I mean, this is linear time, right? And each node gets visited once, each edge gets visited at most once. So I'm really not worried. Maybe it's just that we do this thing multiple times. I mean, you could do this like as part of this in a global variable, which we kind of already have. So I don't know. Would that be faster? I'm actually just curious for science whether that'll be faster. I think this is actually a little bit yucky, but yeah, so you could maybe do something like that, right? Actually, this should be here. Should be here actually. Right, so then now we could get rid. Well, that part we want, but yeah, and oh no, I mean no, it has to be. Even if you don't visit it, you have to do it. The reason is because, like we said, here you may not visit 2 twice, but you still have to do it. Okay, is it faster? I'm just curious as to see whether this is an optimization or not. And it turns out it's about the same time, which honestly does not surprise me. But I'm wondering how it could be faster. I mean, I don't think union find would be that much faster. I mean, my only guess is that the recursion for 10 to the 5th maybe is a little bit slow. It's just a lot on the stack, right? Along with a lot of memory, as you can kind of see actually. So maybe if you do it with breadth first search, it'll be a little bit better. Do I want to do a breadth first search? Let's do it with breadth first search. Why not? Why not? And it's actually a little bit cleaner, the code anyway, because we don't have to do with this current thing, right? Because we can just right. Let's set it here. I don't know. Now we're upsolving a lot, but that's fine. Yeah, okay, so the node is the root. We don't have this. We could just put it inside, right? Here, how do we want to set this up? Yeah, so then here is just we have a queue is equal to collections.counter, right? Oh, sorry, collections.deck. We have a queue. We want to append node, right? Pretty normal stuff. Then while length of queue is greater than 0. I'm curious whether I don't think we need anything else other than visited. So here, actually we should say visited of node is equal to true, so that we don't and we don't put the same node in the queue more than once. Maybe I'll just put current just because it's that's my style. And then for w in adjacency list of current, right? No matter what, as we said. So if not visited of we, which actually I guess it implies parent is not used anyway. If it's not visited, then we should visit it. So q.append we and visited we is equal to true, so we don't do it again. Yeah, and also we want to, that means that when we process, we want to root subcurrent is equal to node, right? I think that should be good. Oops. This is not cost of I, it's cost of node, but yeah, I mean, where visit is, yeah, I probably call visit some, oh, oops, yeah, we don't need the parent anymore. I mean, these 2 cases are fast. Still good to see they run. I mean, you can see that this is a good % faster and a good memory less. I'm curious what is so fast about the other ways. What did I do last time? When was the last time? I don't even know. Apparently, I tried it with different ways last time, and it was much slower. It was almost a year ago now. Huh. Less memory though, and I did do it with Union Find as I thought I would. Is there a better way? Why? How are people so fast? I'm curious. Like what is it just hacks? I mean, this is union fine, I suppose. And this is BFS. Is my BFS too slow? I don't know. Honestly, is a little. I think my code is pretty clean, but maybe not. How do I get back to my code? I don't need to. Oh, there we go. Yeah. I mean, I feel like this is pretty okay. I don't know. It is actually a little bit surprising to me. Could I have done a little bit better? I mean, this is so tight. I don't know how that other goes faster. I don't know. Maybe just Leetcode things, but you know, it's fine, right? I mean, the only way that right now we pre-process everything, right? I guess one way that you can do it is not pre-processing everything. And what I mean by that is that you can also just, which is, I don't know. What I mean is that instead of pre-processing, instead of here, we go, yeah, like if not visited of you, then visit you. If not visited of we, then visit we, something like this, right? And then now it would get that. But as a benefit, if you will, is that we don't need to have this. But so then now you don't run the code that doesn't, like, you don't pre-process the stuff that don't happen. But yeah, it doesn't seem like it changes that much. Honestly, I'm a little bit surprised. Maybe it's just like, I usually don't care about this, and I honestly don't care that much. But I am curious whether there's like a learning thing here. Like, what am I doing that is slow? If you know in the comments, let me know. But yeah, like, I honestly, like, now I feel like everything I do is, I mean, it's before it was linear in terms of edges plus query. Now it's still linear. It's just that we made some small adjustments. Can you imagine that much more? I mean, I guess maybe the adjacency list, in the sense that if you do a union find instead on them, like, you don't, if you can convert them, but I don't know, that may be the only thing that is, like, I don't think I could strip anything else really, right? So I don't know. Yeah, I don't know. I mean, this just looks like pretty much what we're doing, except for nuts. DSU, we had DSU before. I don't know. Maybe I'm fine. All right. Anyway, that is all I have for this one. Like I said, this is linear time. You know, for each node, we only visit each node once and also each edge once, and we only do O of one working query. So everything is O of n plus q, where n is the number of edges in this case. And yeah. That's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.